Hey guys, it's Shakya and welcome back to my YouTube channel. In today's video, I'll be talking about space complexity. So what is space complexity? So space complexity is the total amount of memory that is needed by an algorithm to execute. So this includes both the auxiliary space and the input space. So we'll take a look at those two terms in a bit. So first, what is the difference between time complexity and space complexity? So time complexity is the total amount of time that an algorithm takes for it to execute. And space complexity is the total amount of memory that an algorithm requires to execute. So time complexity answers the question how fast is the algorithm, and space complexity answers the question how much memory does it need. So why is space complexity important? So in computer devices, space is not unlimited. There is a finite amount of memory available. So it is important that we manage this limited memory efficiently. So if an algorithm executes fast but is memory inefficient, then the algorithm would fail. And also, if there is a large amount of input, we have to manage the memory accordingly. So this is why space complexity is important. So now let's take a look at a few types of memory used in programs. So there's stack memory, so this includes function calls, local variables, recursive calls, and then there's heap memory. So this is the dynamic memory allocation, objects, arrays, linked lists. So then we have code space. So this is the memory used to store the program itself. And then there's static space, which is used to store the global variables and the static variables. Okay, so now let's take a look at what input space is and what auxiliary space is. So input space is the memory required to store input data. So imagine we have an array of size n as the input data. So this would require an n amount of input space. So auxiliary space is the extra or temporary space that an algorithm requires during its execution. So this is temporary variables, extra arrays, or recursion stacks. So let's imagine we need to reverse an array. So in order to reverse an array, the program would get an extra temporary array as well. So that is an example of auxiliary space. Okay, so just as in time complexity, space complexity also uses big O notation. So it describes how memory grows as the input size grows. So we have O1, which is constant space, On, which is linear space, On squared, which is quadratic space, and O log n, that is logarithmic space. So let's take a look at each one of these in detail. So On1, that is constant space. So this requires a fixed amount of memory. That means that the memory doesn't grow with the input size. So for example, finding the maximum value in an array iteratively, binary search, and all of these require constant space. So then we have On, which is linear space. So this means that the memory grows with input. So for example, storing data in an array, in a linked list, and most data structures also have an On space complexity, and also in merge sort, and On squared, that is quadratic space. So this can be seen usually from 2D arrays or matrices. So in the example, We can see a matrix of n by n. So here you can see a table of the basic data structures and its space complexities. So simple variables and pointers have an O1 space complexity. Arrays, linked lists, stacks, queues, and hash tables have an ON space complexity. Recursive factorials, Fibonacci and all have an ON space complexity. And 2D arrays, adjacency matrices and all have an ON squared space complexity. So if we talk about the space complexity of recursive algorithms, a recursion uses a call stack memory. So each recursive call would stay in the memory until the function returns. So the space complexity of a recursion would be ON because it uses the call stack. So even if no extra arrays are used, the recursion itself would consume memory. So how can we analyze the space complexity? So first of all, we have to ignore the constants, because if there are constants, it means that the space complexity is O1. And then we can count the input storage, that is arrays, strings, matrices, and all. Then we can count the extra data structures like temporary arrays, stacks, or hash maps. And then we have to consider the recursion depth, like each recursive call would require stack space. And then we can take the largest term, that would be the final space complexity. So let's take a look at an example. So here, we have three variables here, int a, int b, and int sum. So let's say that int a requires 4 bytes. And let's assume that int b also requires 4 bytes. And again, let's assume that sum also requires 4 bytes. So here, a small amount of auxiliary space will also be used to this. So let's say in this system out, so let's say that it also requires 4 bytes. So then we get a total space of 16 bytes. So regardless of what this int a is, let's say int a is 15. Even though it is 15, it would still only require 4 bytes. So all of these variables are constants. So this has a space complexity of O1. So let's take a look at another example. So here I'll be copying an array. So as an input, I have taken an array, and the length of it will be stored in the n variable. And then I'll be creating a new array with the length of the input array. So here the memory of the new array would depend on the input array. So let's assume that one integer needs a memory of 4 bytes, and there's an n amount of integers in this array. So the memory required for the new array would be n into 4, which is 4n, and we can ignore the constant 4. So this means that this has a space complexity of On, because the memory required for the new array depends on the number of values in the input array. And that is it about space complexity. I hope you guys understood today's video. If you guys have any questions, feel free to drop them down in the comments below. Thanks for watching, and I'll see you in my next video.